Imagine NASA interrupts every broadcast on Earth with an impossible announcement. A massive black hole has suddenly entered our solar system, and our planet is already drifting toward it. The immediate panic would likely be driven by a persistent pop culture myth, the idea that a black hole acts like a giant cosmic vacuum cleaner, aggressively sucking up planets, ships, and stars as it moves through space. But this diagram comparing a normal star to a black hole shows how they actually operate. Instead of a suction device, a black hole is an infinitely deep well of highly concentrated gravity. If you don't cross its specific threshold, you can safely orbit it just like any other dense object. To figure out exactly what happens to Earth in this scenario, we have to track our spatial, step-by-step descent toward this anomaly. Walking through this doomsday timeline gives scientists a way to test how gravity dictates the rules of the universe when pushed to its absolute limits. The first warning signs wouldn't be visual. Deep inside mission control, scientists would start detecting subtle, inexplicable errors in their celestial measurements. Long before the black hole got physically close to Earth, its immense mass would reach out and tug on our planet, invisibly disrupting our orbit. Astronomers would immediately scramble deep space telemetry and reposition satellites, racing to map the trajectory of this invisible threat. Earth's stable orbit breaks down, elongating sharply toward an invisible center of gravity. Our planet swings closer to the sun, then further away, causing rapid climate shifts from flash-freezing oceans to boiling heat waves. Simultaneously, massive tidal forces bulge oceans outward, drowning coastlines. Humanity wouldn't even need to fall into the black hole. The complete destabilization of our solar system's delicate gravitational balance would be enough to end life. But if you managed to survive the orbital chaos and looked up at the sky, you'd witness the laws of physics breaking down in real time. The black hole's gravity is so intense that it physically bends the path of passing light rays, a phenomenon known as gravitational lensing. The starlight traveling toward Earth gets caught in this gravitational drag. Familiar constellations smear into bright, stretched arcs, and the light from distant galaxies duplicates itself, framing a pitch-black void. This optical illusion completely scrambles our view of the cosmos. Every celestial object you see is a mirage, hiding its true position behind a wall of bent light. As Earth makes its final approach toward the edge of the void, we encounter a hard limit in the mechanics of the universe. This diagram maps the event horizon, the literal point of no return. Particles outside the boundary can escape, but once anything crosses that line, it spirals inward forever. Escaping here requires moving faster than the speed of light, which is physically impossible. Crossing the event horizon cuts Earth off from the rest of the cosmos. For anyone on the surface, observable physics stops working, and the universe simply ceases to exist. The warped sky collapses into a single pinpoint of starlight, and then absolute silence. Our planet is entirely swallowed by the darkness. Fortunately, astronomers are actively mapping our stellar neighborhood, and there is zero observational evidence of a black hole heading toward us. Scientists don't run these simulations to prep for an impossible doomsday. They use these extreme hypothetical events to pressure test our theoretical models of physics. By calculating exactly how a planet would be torn apart, or how light bends around a void, we build a more accurate map of the everyday forces of gravity shaping our own world. Which phase of this descent do you think would be the most terrifying? The tidal waves or the distorted sky? Let us know in the comments and subscribe for more deep dives into the mechanics of the cosmos.